Alright, so I think we're recording. Let's take a look at this review for our upcoming test. Here we have a quadratic equation. Every quadratic equation can be solved by using the quadratic formula or by completing the square, and some quadratic formulas can be factored. In general, if you can factor it, it's usually a little bit faster solution. So let's take a look at this. We've got, let's get it in standard form. 5y squared minus 14y plus 8. I don't see any greatest common factor through here. The Algebra 1 team here at Northview teaches this method that's referred to as the X. They refer to it as the X method. It's just a way to illustrate the distributive property. Take the first term times the last term and place it on the top of this X. You draw your X over the middle term. Be careful if you have a negative sign that you don't draw it through the negative sign and accidentally later read it as plus 14y. So here are two numbers that multiply together to give me a positive number but add to give me a negative number. Both are going to be negative, and I believe that negative 10y and negative 4y do the trick. So then they suggest, since they illustrate the distributive property when they multiply binomials by constructing a table, since we're factoring this trinomial into a product of binomials, we work from the inside of the table outward. We enter the table diagonally with the first term and the last term, and along the other diagonal the values that you found from your X. When this diagonal has both negative signs and this positive, then when I look here horizontally, I'm going to say that negative 2 divides both of those values, and when I look at this vertically, negative 4 divides both of those, and then negative 2 times a negative 4 is a positive 8. If I look horizontally across here, they only have a y in common, and if I look vertically here, they have a 5y in common, and you can multiply the row and the column and see that that's how the table would be filled out. So that allows you to come over and say y minus 2 and 5y minus 4. Now some of you are good enough with mental arithmetic and good enough at factoring that you can basically do that, visualize it in your head. When this first number is a prime number, the only way to get 5y squared is 1y times 5y, and there's not a lot of different factors of 8, so just sitting there thinking of the various combinations, people can usually arrive across it pretty quickly. It's when this number is a composite number and has a lot of factors, and the same with that this table method does help in those situations when you have very large numbers to factor. There won't be large numbers to factor on the test, however. It'll be very much like the problems that we're doing here in the review. Here we have a radical equation. On the left hand side we have a single term. On the right hand side a single term. You want to get the term that contains the radical by itself, and then you can square both sides. When you have a constant out there, don't forget to square it. The 3 squared is 9. When you square a radical, you just get what's underneath there. And 18 squared, I think, is 324. Let me check that real quick. Pretty sure it is. Yeah. Alright, so let's distribute the 9. Two-step equation, let's subtract 9 and then divide by 45. So I'm getting a possible solution of 7. I say possible because with the radicals and with the rational equations you have to check for extraneous. What we solved is a solution to this equation, but it may not be a solution to the original equation. Alright, so if let's just check it on the calculator. If we plug in 7 on the left hand side and do the arithmetic, if we get 18 it checks. If we get something different than 18 it doesn't. Of course, unless we've keyed it in wrong or made a silly error, but so I should get 18, and I do. So this checks, and we're good here. All right, so we have a rational equation. But again, just like the radical equations, we need to check our answers for extraneous solutions. Here we have a proportion, the claim that one ratio is equal to another. So this is a time that you can actually cross multiply. You're crossing over the equality, so the equal sign. Let's take 10 times the quantity a minus 2, and let's take a times the quantity 2a minus 3. So if I distribute that, what do I get? I get 10a minus 20, 2a squared minus 3a, and I have a quadratic equation. Let's get it in standard form. We've got 2a squared minus 13a plus 20. You can always use the quadratic formula, but I believe this will factor. Again, if you draw an x over the middle term, the first term times the last term is 40a squared, and a negative 8a negative 5 should do the trick, because that product is negative 8 times negative 5 is 40, but negative 8 plus negative 5 is negative 13. They suggest that you draw a table. You enter the table diagonally, putting the first term and last term along one diagonal and the values of your x along the other. And you can diagonally, you could exchange those terms, and you'd still get the right answer. But you do want to enter them on the table diagonally. I can see here this diagonal is negative and negative. This is positive. So when I factor this here, I'm going to say that negative 4 divides both of those terms. Negative 5 divides both of those terms. When I look horizontally here, the 2 and negative 5 are relatively prime, but they both have a common factor of a. Here, these are both even numbers, and they contain an a. So I'm getting that I can factor this to a minus 4 and to a minus 5. So by the zero product rule of two or more things multiply together to give you 0, then one or more of the factors have to be 0. So if a minus 4 is 0, that results in a equal 4. If 2a minus 5 equals 0, that results in 5 divided by 2. And because it's a rational equation, we need to check and see if the left-hand side equals the right-hand side when we plug in values. So if we're plugging in 4, on the left-hand side we have 10 divided by, if we plug in 4, we've got, 8 minus 3, and that's 5, and 10 divided by 5 is 2. And on the right-hand side, if we plug in 4, we've got 4 divided by, 4 minus 2 is 2, and 4 divided by 2 is also 2. So I don't need the calculator really to check that. On the other one, if I have 10 divided by, again, 2 times this 5 halves, the 2 would cancel, and 5 minus 3 is 2, and 10 divided by 2 is 5. Let's plug it in here now. Here, if you want, we can, on the right-hand side, get 5 halves. Suppose you could have just keyed it in as 2.5. And we get 5 as well. Remember that the 2's canceled. 5 minus 3 was 2, and 10 divided by 2 is 5. And on the right-hand side, it's 5. So both of those check, and those are solutions to this rational equation. Be careful here, this is a quadratic, but it's not set equal to 0. Don't come in and set the individual factors equal to 0. That zero product theorem says that you have to have 0 on the right-hand side. So I have no choice but to multiply this out and get it in a standard form. and then look and see what I have. Either complete the square quadratic formula or factor if we can. We've got x squared plus 3x minus 6x minus 3x minus 18 equals 52. If I subtract the 52 from each side, what do I get? I think, is that 70? Yeah. And if I factor that, yeah. With a 1 as a leading coefficient, you don't necessarily have to do that x method. Its primary advantage is when that leading coefficient is a large number that's not prime. Here we can see that x times x gives you x squared, and that negative 10 and positive 7 give us the negative 70 that we were looking for, and if you add those together you get negative 3. This gives us solutions of 10 and negative 7. Now, I don't have to check, quadratic equations, we don't have to worry about extraneous solutions. We only have to worry about extraneous solutions if the original equation is a rational equation or a radical equation. And then later in another skill packet, we see some other situations like with logarithms and stuff that you might get extraneous, but we'll worry about that when we get there. Let's take a look and see here. We've got this rational equation. I'm going to subtract 2 from both sides just to, and write the 3 as 3 over 1. I've got 9 over x minus 2. Be careful, you don't have a proportion. You cannot cross multiply because of this term of 3 over here. So we can see that this 1, that we need a common denominator of x minus 2. So if we multiply this first term by the number 1, but if we write 1 as x minus 2 over x minus 2, now all of these denominators are x minus 2. And if you multiply by that least common denominator, then all the denominators will be clear. Every term, if you multiply by the x minus 2, then this equation will be clear to the denominators, and we'll just have 3 times x minus 2 plus 9 is equal to x plus 7. Now, however, this equation is not like the original equation. It doesn't have a variable in the denominator. The solutions to this equation may not be solutions to the original equation. That's why we have to check for extraneous. When you multiply both sides of the equation by a variable, you introduced maybe some extra solutions to this equation that the original one doesn't have. That's why we're checking. So here, just get x by itself. And if you forgot to check this, you would say that's a solution, but I can see just by inspection that 2 minus 2 gives me a 0 in the denominator. And oftentimes I believe that a lot of teachers will tell you to look at these rational equations and just right off the bat over to the side write down that x can equal 2. Over to the side, where was the other one? We could have written down that a had better not be 2, or that a had better not be 3 halves, because those would have caused division by 0, and you can write that right off the bat to check and see. Make sure your solution. So our final answer here is a no solution. That was the only candidate, and when it didn't check, we have the empty set, which no solution here. Now, we have a radical equation, but the index is odd. This will not produce extraneous solutions. When I get my solution, I don't have to, the technique doesn't require that I check it. I may want to check it just for my own accuracy to make sure I don't make any silly type of errors, but the technique of solving this equation, because see, we can take the cube root of negative values, the even root of negative values, we don't have has no real solution. So if we cube the left hand side, because that's what the index is, and if we cube the right hand side, we get 6x plus 9, 4x minus 3. If I subtract 4x from each side, if I subtract 9 from each side, I'm getting that x is negative 6. And like I say, I don't have to check it. I can check it real quick just to make sure. If I plug in the negative 6, I've got negative, 36? Yeah, 6 times a negative 6 plus 9. I get a negative 27, and the cube root of negative 27 is negative 3. On the right hand side, you get a negative 27 as well, because you get negative 24 minus 3. So negative 3 equals negative 3, and it would check. But like I say, the technique doesn't require it because that's an odd index. Here we have a rational equation. We can look and see that we had better not get x equal negative 2 or x equal to positive 3 as a solution. We would call those extraneous solutions. When you're factoring these, oftentimes you'll see one or more of the factors over in the other denominators, because they do that, otherwise it's just a longer problem. If I factor this left-hand side, or the first term, the denominator of the first term on the left-hand side, I get x minus 3, x plus 2, which does happen to be those other factors. So now if I can look at the denominators, I can see what's missing. I can see this term is missing an x minus 3, so I can come in and multiply by the number 1, but I'll write the number 1 as x minus 3 over x minus 3. Then I've got 2 over x plus 2. Oh, I'm writing the same one over again. X over x minus 3. And this guy is missing an x plus 2. And of course, with the 0, if you want to see that denominator, 0 in the numerator is okay, because 0 divided by this x minus 3, x plus 2 is just 0. So with all of these denominators the same, if we multiplied every term by that least common denominator, we would clear the fractions of this equation, and we're just working with the numerator. But when we go to solve for this equation, it may not have the same solution set as the original equation. It may have some extra solutions, and that's because we multiplied both sides of the equation by a variable, by the least common denominator that contained a variable. So this is a quadratic equation. Let's get it in standard form. We know it's quadratic because right here the x times x gives you x squared. Oops. I can hear the band practice in the hallway. I doubt if the mic can pick it up. Saturday morning they had some you guys slept over last night, and I came in the mornings a little bit after you got up, and I think you were down there having breakfast. Alright, so this factors to x plus 5, x minus 1. That gives me possible solutions of negative 5 and positive 1. Let's come in and look and see if we plug in a negative 5 into all of this, does it add up to 0? So my first fraction here, if I square a negative 5, I've got 25. If I subtract a negative 5, that's like adding 5. And then it says minus 6. Now notice I put parentheses around my entire denominator. Now my second fraction, 2 divided by, and again, the negative 5 plus 2 is a negative 3. And then plus the numerator's x, and we're plugging in negative 5 for x. And the denominator, negative 5 minus 3 is a negative 8. And if this is a solution, we get 0, so yeah, that checks. If we plug in 1, what do we get? Well, 1 minus 1 cancels right there, and we've got a negative 6. We've got plus 2 divided by, if we plug in 1 plus 2 is 3. If x is 1, that numerator is 1, and the denominator, 1 minus 3 is a negative 2, and that checks as well. So these are, both of these checked. They're both in my solution set to my original equation, that rational equation. If we look here, we've got a radical equation. We have to make sure that the term that contains a radical is isolated, and it is there on the left-hand side. So we're ready to square both sides of the equation. It's incorrect to say that the radical cancels. It's because of properties of radicals of why we say that radical goes away, but that's just a technicality, right? If I square this binomial, I have 1 minus 6x plus 9x squared. I have a quadratic equation. Let's go ahead and get that in some kind of in our standard form. And so I've got 0 is equal to 9x squared minus 9x plus 2. So I think that'll factor. If it doesn't, we can, you do need to know the quadratic formula. If we place an x over this, the first term times the last term is 18x squared. And what do we have? We've got a negative 6x and a negative 3x will do the job, because negative times negative is positive. We add these together, we get the middle term. The algebra team then taught students to put this in the form of a table where the first term and the last term go along one diagonal, and the two values you found in the x go along the other diagonal. When this diagonal has both negative signs, and that's positive, when I factor this out, I'm going to use a negative 2. Both of those are even values. Here, just a negative 1, and a negative times a negative is positive. When I look horizontally here, I'll factor out a 3 and an x, because 3 divides both of them. X, it's common to both. I'm pulling out the greatest common factor is what I should be saying. Alright, here vertically I have another 3x, so we can see if you check by multiplication, these outside, if you take the row times the column, you'll get that corresponding entry, and we have 3x minus 2 and 3x minus 1 for possible solutions of 2/3 and 1/3 if I haven't made any silly type of errors. Now let's check these and see. Remember, right now I'm not ready to say that they're my solution yet. I want to check them. I can do that in the calculator. If I, on the left hand side, we're taking the square root of 3 times this 2/3. Well, the 3's cancel and I just have 2, and 2 minus 1 is 1, so on the left hand side I just have 1. And the question is, on the other side, if I plug in 2/3, well, that 3 and this 3 cancel, and 1 minus 2 is a negative 1. So this is extraneous. It does not check, so I don't include it in my solution set. If I plug in 1/3, 1/3 of 3 is 1, and 1 minus 1 is 0, so I'm getting a 0 on the left hand side. And the question is, if we plug in 1/3 here, will we get a 0? Well, 1/3 of 3 is 1, and 1 minus 1 is 0. So this one checks, but the 2/3 did not check. To get full credit, you've got to recognize when you have extraneous solutions. Number 9 is a rational equation. Look at the denominators, write it in factored form. That way you can see what common denominator you want to every term. We can see pretty easily that an x factors there, and that we have x minus 3, so that's going to be the common denominator we want everywhere. So to save a little bit of writing, let's just recognize that right off the bat. And we've got x minus 3 over x minus 3 is the number 1, and now that has the denominator that we want, 8 over x minus 3, and if we multiply by the number 1 but write it as x over x, here I'll put the x out in front, and then I could have written the multiplication is commutative. You can multiply real numbers in any order, and we said that we noticed that an x was common and that factors to x times x minus 3. So we have a common denominator everywhere. If we were to multiply both sides of this equation, when you multiply every term by that least common denominator, you clear the fractions and all you have left is the operations in the numerator. But in multiplying both sides of the equation by a variable, you introduce the possibility of extra solutions, extraneous solutions to the original equation. So the solutions to this equation may not be solutions to the original equation. We have to check and see if they are. So if I haven't made any silly mistakes here, which I am definitely prone to do, divide both sides by 12, I get 3. Oh, look at there, 3 minus 3 does cause me division by 0, so this is extraneous, and that was the only candidate, so I have the empty set. So this equation has no solution. Alright, we have a radical equation. This time it contains 2 radicals and another term. So this one you might slow down a little bit and think about. First, make sure that you don't have both of the radicals on the same side of the equation. You have to have the term that contains a radical by itself. And I don't think there's any real extreme advantage of having one of them. I suppose you would want the more complicated one that is solved for, but they're generally not that much of a difference. X plus 21 and x, yeah, I suppose you could say that x plus 21 is technically more complicated just because it has 2 terms versus the x. Let's square both sides of the equation. When you square the radical, it goes away. And remember, the exponents don't distribute, that this means 3 plus radical x times 3 plus radical x. So however you learned how to multiply binomials together. Now remember, if someone taught you FOIL, that only works for binomials. What you're really doing here is a mathematical property called the distributive property, that multiplication distributes over addition or subtraction. For some people, again, multiplication, using that distributive property, an organized way to apply it is to do it in the form of a table. This time we're not factoring, we're going to fill in the inside entries since we're multiplying. So the 3 times 3 gives me 9. Be careful, don't write 6. Don't accidentally add when you intend to multiply. If you're tired or if you're going too fast, you'll have a tendency to do those things. And here, when you multiply the radical goes away. So along this diagonal, we have like terms. We have 3 of these things plus another 3 of those things for a total of 6 of these radical x's. On the left-hand side, we have x plus 21. On the right-hand side, well, that diagonal gives me 9 plus x, and this other diagonal gives me the 6 radical x. So when I look at this new equation, it only contains 1 radical, where the original equation contained 2 radicals. So by squaring it, it is simpler than when we started. The technique now, it's repetitive. You do the same thing. You get the term that contained the radical by itself, and you square both sides of the equation again. Now this time it simplifies kind of nice, because if we subtract x from both sides, those x's cancel, and we've got 21 minus 9, which I think is 12, and then we have the 6 radical x. Now I can come in and square both sides fine, as long as I remember to square the 6, but since both of these values, I can divide both sides by 6 and just make the number smaller. Well, here I can see just by inspection that the principal square root of 4 is 2. I can see that x equals 4 is the solution. If you have to square both sides, go ahead and do it, but it should be obvious when you have 2 equals square root of x that x is 4. Let's check, and it's obvious that it checks as well, because 4 plus 21 is 25, and the square root of 25 is 5, and 3 plus 2 is 5, because the square root of 4 is 2. So this guy checks. You know, in a way, it's a lot of work to get something that some people could look at, and just by guessing, 21 is real close to a perfect square, and if x were 4, and hey, 4 is a perfect square, now that you see the solution here, and you look at the equation, you're like, man, I could have almost guessed that without all this work. But you need to show your work to illustrate that you understand, because not all the answers are going to be that easy that you can just look at it and solve by inspection. So here we have a quadratic equation, pretty straightforward. We don't even have a linear term, so we'll get x squared by itself. So if I subtract 2x squared from each side, if I subtract 7 from each side, if I divide by 4, and positive or negative square root of 5 is the solution there. Now, in completing the square, you've got a 5-step process. I gave you an additional page of notes with that skill packet that had things about the discriminant on there and this completing the square. So the first thing that we notice is that the variables are on the left-hand side and the constant is on the right. Sometimes you'll have to move that constant term to get that first step accomplished. We need a coefficient of 1. So the first thing we need to do for this problem is divide everything by 3, and the numbers work out kind of nice here. X squared minus 8x is equal to negative 3. I'm going to move that a little bit over here to give myself some room. So then the thing to remember about completing the square is you take half of that linear coefficient term, half of this term, and then square it and add that to both sides. That's an easy thing to do if this number is an even number. If it's an odd number, a little more difficult. If it's a fraction, all of a sudden students find it. But no matter what kind of number it is, you're dividing it by 2, and then you're squaring that amount and adding that to both sides. So half of negative 8 is negative 4, and see that's what my perfect square is going to square to, is by taking half of that middle term. Now, in order to get that to work out, like if you multiplied a negative 4 times a negative 4, hey, that's positive 16. I mean, that's why that we're taking half of that, because this is always going to be half of that, and then that squared. So you know, I question whether sometimes people make that connection or not. I've seen that pattern. So if I haven't made a silly mistake, I get 13. When I extract the square roots, I put plus or minus here because the variable on the left, and add 4 to each side, and we're done. We've got our two solutions. If they had given me a radical, say, that was like 12 rather than 13, I would have had to have recognized that 12 is the same thing as radical 4 times radical 3, which is 2 radical 3. You are expected to simplify radicals, or to write fractions in lowest terms, or to simplify your answers. And you have to show these steps in order to get full credit. Alright, so here we have a system of equations. They're not linear equations. We have a parabola and a line, and I think I showed you I sketched the picture on these graphing calculators. X squared plus 2x minus 5. That's going to be a parabola that opens upward. This negative 3x plus 19 is a line, and it's going to intersect that parabola probably twice. Okay, I'll have to zoom out to illustrate that. Boy, that really zoomed out. Yeah, but we can see it's intersecting it somewhere up here and over there. So this is set up nice for substitution. Call this equation 1, call this equation 2. We're going to sub equation 2 into equation 1. By that I mean everywhere we see a y in equation 1, we're going to replace it with negative 3x plus 19. So we've got negative 3x plus 19 is equal to x squared plus 2x minus 5. That's a quadratic equation. Get it in standard form. X squared, add 3x, I've got 5. Subtract, and that's 24. That can easily be factored. So here's where many of my students have made mistakes in solving this, that they stop here. They're happy that they got x equals negative 8 and x equals 3, but remember that you had a parabola. You want an x and a y for that point and an x and a y for that point, so we've got to plug it in. Well, it's set up nicely to determine the corresponding y value, because all you have to do to get the y value, plug in negative 8 here and do this arithmetic. So we've got negative 3 times the negative 8 plus 19, 24 plus 19, 43, right? Yeah. And here, negative 3. Negative 3 times a positive 3 plus 19, negative 9, hey, that's 10. So one solution is negative 8 comma 43, and the other point has coordinates 3 comma 10. And I suppose it's common that we order them x comma y. Sometimes if you have different variables than x and y, a and b, people might put it in alphabetical order, but you'll want to tell people how you ordered it. For Cartesian coordinates, when you're working in the plane, it's common that we use x and y, and it's common that x is the independent variable and y is the dependent variable, and that we order it x comma y. Alright, so there's the solution for 13. Here we have a system of 3 by 3 linear equations. So this is working in three-dimensional space, and the idea here, I'm going to do it by elimination, and that's the way I suggest that you do it as well. And I'm going to pick a variable to eliminate. There's no wrong answer to eliminate, but what typically I'll look for is I'll look for leading coefficients of 1, like the x's here would be easy to cancel. With a positive 1 and negative 1, I'm immediately drawn to eliminating the z's first, so let's do that. Like I say, there's no wrong answer. Let's eliminate the z's by taking equation 2 plus equation 3, and then I'm going to have to do it again to eliminate the z's. And this time I have to use equation 1, and since that's negative, let's use equation 2, but we'll have to multiply equation 2 by 2 in order to get a positive 2 and negative 2. So here, that's just my plan of attack. I'm going to add equations 2 and 3 together. I've got 2x minus 3y plus 1z is equal to 17. I've got 1x, 2y's minus 1z is negative 4. When I add these equations together, try not to make silly arithmetic errors. The z's are eliminated, and that was my goal. I'm going to call this new equation equation 4. Now I'm going to take equation 1, and I'm still eliminating the same variable z. I have a negative 2z, so I need equal and opposite to cancel the z, so I need a positive 2z down here. That's how I recognize that I'm going to have to take equation 2 and multiply it by positive 2. I could take equation 3 and multiply it by negative 2 and you know, because we have to use equation 1 because we used equation 3, but we can use 1 and 2 or 1 and 3 in this second pair. Alright, so let's try to double these without making any silly mistakes. If I double 17, I get 34. So I've got 5x minus, here I put, you don't have to put ones there, just sometimes some students just like the comfort of visually seeing that 1 as a coefficient. So this is my equation 5, but I notice that everybody's divisible by 5, so just to get the value smaller, I'm going to divide every term by 5, and now I'm going to call that equation 4. So let's see if I can give myself some more room by going to another page. Let's see if we can't copy and bring these equations along with us. Sometimes it cooperates, sometimes it doesn't. So there's my equation 4. Let's bring my equation 5. See, it's not going to, well, we'll just take the whole thing and erase what we don't need. Alright. I need to make a decision. Do I want to eliminate x or do I want to eliminate y? Well, since I have a negative 1y and a negative 1y, if I just change the sign in this equation number 5, then I'll be able to add these equations together. So if we multiply this equation everywhere by a negative 1, we'll have negative 1x there. That'll be positive, and this 7 will become a negative 7. And now we can add these two equations, together. And I've got 2x. The y's cancel. 13 minus 7, 6. So I have the x is equal to 3. Now I can use either equation 4 or equation 5 to get y. Let's go ahead and use this 5. If I take the opposite of 3 plus y, I get negative 7. So y is equal to a negative 4. Now to figure out the z, I have to go back and pick one of my original equations because those three equations were the only, we eliminated z right off the bat. So I'm just going to take this whole thing. It doesn't matter which of these equations I pick, so let's just pick that third equation. It says x plus 2y, x is 3, 2y is going to be a negative 8, minus z is equal to negative 4. So we've got 3 plus a negative 8, that's a negative 5. So this guy, z, is a negative 1 because if you subtract negative 1, it's the same as adding 1, and negative 5 plus 1 is, or just, add 5 and divide by negative 1, and you'll see that z is negative 1. So these three lines, in three-dimensional space, that line, that axis z is coming out of your paper is typically how they describe that. And they give a tripled pair, an ordered triple. A pair is two things, so I can't have a tripled pair. Gosh, I'm stupid. 3, negative 4, negative 1 is what I'm getting for my final solution here. So these can sometimes be a little bit longer than the other problems, so you want to, on the exam, be aware of that and move quickly and stuff to, I'm not going to give you ones that you shouldn't get any fractions. They should be integer values. I'm not trying to trick you. You're not going to get some ugly 1 over 127, as one of the answers, and you can quickly plug in and check your work, plug in these, you can use the calculator and plug in the equations, or just check one or two of the equations. Sometimes it is possible to satisfy the top equation and still be incorrect, that it doesn't satisfy the other two. But hey, at least, that's an odd circumstance. Normally, if you check one or two of the equations, you can quickly say, hey, it's going to check, even without checking the third one. But really, they can come up with, the unusual cases where you to check it. Now, the technique does not say that we have to check. It's not an extraneous solution type of situation. And I'm not going to give you one that's a no solution or infinitely many solutions and stuff. These three lines are going to intersect at a unique point. So here we have one of our distance problems. Julia is able to ride her bike 3 miles in the same time. So when I see that it says same time, that's what I'm drawn towards. Oops. That I have the time that Julia is riding on her bike is equivalent to the time that Donovan is riding his motorcycle. Okay. Now I know the relationship that time is equivalent to distance divided by rate. So I'm going to try and get information about distance and rate about Julia from the problem, and the same with Donovan, the distance and the rate with respect to Donovan. And what it's asking for, how fast does Julie ride her bike? So this is what they're wanting, Julia's rate. This is what we want to our unknown that the problem is asking us for. All right. So the distance that Julia rides her bike, it says, is 3 miles. The distance that Donovan rides his motorcycle is 15 miles. The motorcycle is obviously going to go a lot faster than the bicycle. 30 miles per hour faster than she rides her bike. So if we let X be the rate that Julia rides her bike, that's what we're going to want for our final answer is X. And Donovan is much faster at 30 miles per hour. So now we have a proportion that we can cross multiply, and now we can pretty easily solve this. Along that diagonal and along this diagonal. Along the yellow diagonal, I have 15 times x. Along the other diagonal, I have 3 times that binomial. If I use the distributive property, I have 3x plus 90. If I subtract 3x and divide by 12, remember this is for Julia, and how much, and it's in miles per hour. So 90 divided by 12, 7.5. So she's going 7.5 miles per hour. Alright, let's take a look at this problem. Michael rides this ATV through woods and fields. He spends 2 hours longer riding through the woods than he does the fields. One day he rides a total of 28 miles. So there's our attack right there, that we have this total distance, and it's being split into two parts. The distance that he drives through the woods and the distance that he drives through the field. At least this is my first thought, my first approach when doing this. If it doesn't work out, then we'll come back and see if we can see that with he's not spending the same time in the woods as he is the fields. We can see that he's not going at the same rate, and most of the time we're either setting the distance equal to each other or the time equal to each other. On these type of problems, we usually don't have a situation where we're setting the rates equal to each other. And the total is always a total distance or a total time. It doesn't make sense to speak in terms of a total rate, an average speed. So let's substitute in and see what we have here for the total. We don't know the distance, and it wants to say determine how long he spends in the woods and how long he spends riding. So by how long, it's not saying how far. So I'm going to assume that that's asking for the time in the woods and the time in the field. So keep that in mind. The distance in the woods is the rate times the time in the woods. And the distance in the fields, well, distance is equal to rate times time. That's a dot for the field. All right, so we know how fast he's going through the woods. He must slow down a little bit. Yeah, the 8 miles per hour. And in the fields, he can go faster, 12 miles per hour. He spends 2 hours longer riding through the woods than he does the field. So if I let X be the field, then the woods is longer. How much longer? Well, it says 2 hours longer. So now I have an equation, one equation, one unknown, and I can solve for X. I've got 28 is equal to 8X plus 16 plus 12X. Subtract 16 from each side. Add these together. Divide by 20. I can still hear him out in the hallway, and it's a sound that's going rising and then lowering. So it's if I start laughing, that's why. 4 divides each of these, so 3/5 of an hour, and because that, remember, the X was time, and that's in the field, and in the woods was 2 hours longer, and that's a proper fraction, so we can just write it as a mixed number as 2 3/5. 2 plus 3/5 is 2 3/5, and that's in the woods. I'm here, and then that's funny. All right, let's move on. A mixture problem. How much of a 20% bleach solution must be mixed with pure water? So I have to visualize it. So I almost always have to visualize some container with a concentration. So I've got 20% of this bleach solution is being mixed with water. High quality H2O. And water doesn't have any bleach in it, or at least we hope not. We're trying to create a new solution, and it's 5%. So the water's doing the trick. The water is diluting the 20% down to 5%. Now, we want 10 gallons of this 5%. So this 10 gallons is split up between these two containers. It could be 5 and 5, but I doubt it, But whatever this is, and it's saying how much of the 20%. So I'm going to let that be my unknown, X gallons. If I remove X from this, all I have left is the water. So the water is 10 minus X gallons. In other words, when we add these two algebraic expressions together, the X's cancel. This volume plus this volume does equal 10 gallons. Now, when I work with percents just out of habit, I move the decimal point over 2 places. And here 0 times that is just 0. And here 0.05 times 10. And so I've got 0.20. When I multiply by 10, I move the decimal point over. Hey, that's 1/2. So if I divide, oops, I almost multiplied by, if I divide each side by 0.2, what do I have? I've got I know that you're not going to be able to hear what I'm hearing with that mic, because you guys told me it didn't pick up the band last week when it startled me. 2.5. But I really wish this week that you could hear it. It is a little bit funny. I mean, it's good, but I don't know, when you're doing the math problems inside a school, it's just awkward to hear that. So we need 2.5 gallons of this 20% beach solution to add to our water to create 10 gallons of this desired mixture. All right. So we have another mixture problem. We've got apples and oranges, and we're creating a mixture. So here's my apples. Here's my container of oranges. And when we add them together, there's my mixture. So there's the apples and the oranges. And the apples are, that ingredient is $2.50 per pound. Oranges are $4 per pound. The mix, we're going to sell it at $3 per pound. We have how many pounds of apples? That's going to be my variable X. Must be mixed with 5 pounds of oranges to create this mixture. So if we add X pounds to 5 pounds, we have a X plus 5 pounds. And don't forget, because now in my equation, it's the, if it's the concentration, or here the unit price times the weight. Before it was concentration times volume. I set it up in the picture the same way so that it's always multiplication. So I've got 2.5 times X, 4 times 5, 3 times X plus 5. So you get to here and you're good to go, because this is not difficult to solve. 15 minus 20. Whoa, I say it's not difficult to solve. Did I just make a mistake? Maybe. Slow down. Quit listening to the... So 2.5 plus 20 is equal to 3x plus 15. Let's get x by itself. If I subtract 2.5 from each side, if I subtract 15 from each side, if I divide by 1/2 is to multiply by 2. So if we need 10 pounds of apples in order to create this desired mixture of this apples and oranges that are going to set, we'll have 15 pounds of this mixture at $3 per pound to sell. All right, so we've got people are going out to dinner. George can eat a plate of ribs in 12 minutes. Mike can eat the same plate in 10 minutes. Joe and Terry can each. I remember once when we first had this problem, remember that we had the Jed working on a deck, and we had the team of Ted and Fred, and we looked at that as a single unit because Ted and Fred were working together. But this time it's just saying that they can each eat a plate. So Joe and Terry are separate. They're each individually contributing. They just happen to contribute the same amount towards eating these plate of ribs. So my unit of time is minutes. So how much of the ribs can they eat on a per minute basis? So George can eat 1/12 of the ribs per minute. Mike can eat more at 1/10 per minute, and these guys not as much, 1/15 plus another 1/15, because it does say all four. We want to know how long does it take them, all four of them eating. So it's not like that this Joe and Terry are eating off the same plate, or they're saying, hey, let's go in on this cost together. They're not a team of people, not like a couple that might be with some friends out to dinner somewhere. So if we look here, 60 is probably the least common denominator. Multiply that by 5 over 5. Multiply that by 6 over 6. Those are 2, so 4 times 2, that's going to be 8. And you can have the calculator do that if you don't see what I'm doing, but I think that's just basic arithmetic there. Okay, so 19 over 60, or x is 60 over 19. That's an improper fraction. If I take 60 divided by 19, 3, if I subtract 3, and if I change that to a fraction, 3 and I suppose you could just leave 3 and 3/19 of a minute. Alright. Yeah, that's what the answer key there says. If I can put on there that you could give it as a decimal as the 3.16 if you round it to the nearest hundredth. You know, all these problems can be done on the calculator. If you had came in and taken 1/12 plus 1/10 plus 2 of these 15ths, and then just hit the inverse button, boom, you have your answer there. And if you subtract 3 and convert that to the mixed fraction, that's how I got the 3 and 3/19. Alright. Number 20. So Betty can decorate 12 dozen cookies in 3 hours. With her son's help, she's able to complete the job in 2.5 hours. How long does it take the son working alone? So how long it takes the son working alone, that's going to be my variable x. So if she can do it in 3 hours, she's getting 1/3 of the job done per hour. We don't know what part of the job her son is getting done per hour. We call that x, so it's 1x. And together they have it as 2.5. So we can go to the calculator, and I can show you this is just a quick calculator exercise, that if we take 1 divided by 2.5 minus 1 divided by 3, and then take the inverse of that, we've got 15. So her son working alone is a lot slower. If mom could do it in 3 hours, the same 12 dozen cookies her son does in 15 hours. So we'll call him the slow poke son. Much slower than mom. That's why mom's cookies are probably usually the best. Hey, the last problem. We got Robert Morris that's shooting an arrow from the top of a hill. So here's a hill. Robert Morris is on top of the hill. He's watched some John Wayne movie, and he's shooting arrows off the top of the hill. And of course, he's shooting it at Lexington. That's where UK is at. So that's why I put University of Kentucky. Somebody shooting arrows at Lexington, at Kentucky. All right, maybe they hit Calipari. I'm just kidding. So the height, this negative is a parabola that opens downward. As time passes, the arrow goes up and reaches a maximum height, then comes down and hits the ground. If all this is asking us to do is let the left-hand side be 200 feet, and to solve this quadratic equation. With the numbers like this, it's often going to be decimal numbers, so a lot of times you'll need the quadratic formula, but sometimes they've made the numbers such that we don't. If we have, well, that's 32, isn't it? Alright, so looks like all of those numbers are divisible by 8, so I'm going to do that just to get the number smaller. Well, let's divide by -8 to get that leading coefficient, because maybe I can factor it, I don't know yet. I lost my exponent. 2t squared. I could still hear that going up and down. Plus 4. So yeah, that factors. Like I say, identify A, B, and C and plug it in the quadratic formula. A lot of times these won't factor. I can't remember on the test. Just because this practice one did factor doesn't necessarily mean that the one on the test, it's possible you would have to use a quadratic formula. I'm not sure, but I've got 2t times t. I need this guy to be, that's a -8, another -1 to get -9, so we're getting 1/2 and 4. So this represents seconds. So what's going on? Well, in the picture, immediately after Robert Morris shoots the arrow, a half a second later, he's already on top of a 168-foot hill, so it doesn't take very long to reach the 200. In half a second, the arrow is 200 feet above Lexington. Then it goes up to some maximum height, and on its way down, it passes through a height of 200 feet again. That's why there's two answers. Once as the arrow's on the way up, and then once on the way down. So take a look at these. We'll go over these and have questions ready on Monday, and I'll do my best to answer them. And our test is on Tuesday, and I will talk to you later. Ooh, that's what the sound I'm hearing is.